Today we are discussing the movements of a star as it approaches a black hole. The problem that we are investigating is to determine if it is possible to calculate the mass of a black hole from the position data of an orbiting nearby star using the properties of the momentum principle and the law of universal gravitation. And the result from my model and analysis is that from the position data of a star, it is possible to determine the mass of the black hole that it orbits. To outline this report, I will first discuss the fundamental physics concepts used. I will then explain how these main ideas fit into the Python code. I will discuss the results from the code, and then I'll also ask questions such as what if and what does it mean. The physics models that are relevant to the problem at hand are Newton's second law, or the momentum principle, and the law of universal gravitation. There is only one force acting on the star that we are observing, and that is the gravitational force. This is why universal gravitation is useful. Also, since we are observing the motion of an object and its reaction to a force, the momentum principle is also necessary to predict physical movements of our system. In this problem, it is vital to use the concept that a force applied to a system results in a change in the momentum over time. We can analyze this further by breaking dp dt into two components, dp dt parallel and dp dt perpendicular. The reason we do this is because the system is changing in two different ways. Its speed is changing, but its direction is also changing. By determining these two changes in motion, we can add them to result in the total dp dt, which is also equal to F net. And then from F net, we can use the law of universal gravitation to determine the mass of the black hole. Here are the formulas for the law of universal gravitation and the momentum principle. We can also see dp dt broken up into its parallel and perpendicular components, where the parallel component is responsible for the change in speed, and the perpendicular is responsible for the change in direction. Now, applying these concepts to the Python code, we can see how the code is manipulated to model our system here. We can see here how we broke up the components of dp dt, and then wrote dp dt parallel as the derivative of the magnitude versus time times p hat. One useful concept that we also used in the code was the way in which we wrote dp dt perpendicular here. To make it easier, we just subtracted dp dt parallel from the total dp dt to give us dp dt perpendicular. After running the Python program, we are given data that is necessary to calculate the mass of the black hole. We are given the magnitude of F net, which is here, which corresponds to the print data written here. And then we can determine the position of the star relative to the black hole based on the original data in the CSV file. And the reason that the magnitude of the force is only needed is because we only have to figure out the mass of the black hole. We do not need any sort of direction, so the magnitude works perfectly well. Now, when we do the math, we arrive at the mass of the black hole to be 2.042 e to the 31 kilograms. And this answer was then plugged into the Web of Science section and it was deemed correct. The main reasons this model worked are because we began with the necessary fundamental physics ideas, and then simply followed the procedures needed to determine the value of the unknown variable in our equations. And all the interactions the star had with the surroundings were considered, and we then analyzed its motion through space to determine the force that was making the star move in certain directions. And I found it rather interesting that the mass of the black hole was not that much larger than the mass of the star. Now you may want to ask questions such as what if and what does it mean? So let's imagine the black hole whose mass we found was removed, and a different black hole was placed in the same location. And let's assume the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. Would we be able to tell the difference? The answer is no, we would not be able to tell the difference. The reason this is so is because we determine the force on the star by the black hole simply by the motion of the star. The black hole itself had nothing to do with how we calculated anything about it. We just went from the motion of the star to learn more, so if the motion of the star is the same, the knowledge that we gain is the same as well, and we would therefore not be able to tell the difference. Now I'm going to ask, what does all of this mean? All of this data signifies that we are able to break up dp dt into its components and then apply the data from this to determine F net. The main differences between F net, its perpendicular and parallel components, and dp dt and its perpendicular and parallel components is that dp dt is the result of the net force. Although they are algebraically equal, dp dt is not what causes the net force. The net force is what causes dp dt.